Okay, friction part 2. So we were last looking at an example related to calculating the amount of friction required to get something moving, seeing if Ferd had applied enough, and we used this table that has at least a sampling of materials. Of course, this isn't everything, but you know there's an infinitely long list, pretty much, of different materials, right? And the idea is it's how much friction between these two materials. Okay, and remember there's a static friction, which means you're trying to just get something started. There's a kinetic friction, which means you're continuing to get something moving, keep something moving, and that's what the S and the K. Mu is a measure of stickiness between surfaces, right? So ice on ice, for example, is relatively low. Rubber on concrete, a lot higher. Okay, and then wet concrete would be less friction than dry concrete. And of course, anyone who's driven knows that. So we went through this example. That was the end of the last note. Just finishing off the note with a last big example, or talking about what if it's the coefficient of friction you're trying to find. Because obviously we have that big table. But, for example, in your laboratory, I want you to find the coefficient of friction between your running shoe, or your shoe, whatever you're wearing, and the lab bench, right? So in that case, you know, chances are you can't just Google your particular shoe, and your shoe might be really dirty or wore down. Like, you know, it's nice to have a table for sort of a generic number, but it's not going to be specific to any given item. And so if you wanted to find the coefficient of friction between a specific item, two specific items, I should say, our lab bench and your shoe, for example, this is how you would do it. And of course, what does that mean? Well, first of all, this is the force. That would be a friction force, or the force required to move something at a constant pace if you're looking at kinetic friction, or the force required just to start something moving if you're looking at static friction. So if I had a little s right here, then I would be putting Fs right here, meaning I'd be looking at the force required to start something moving. I think in your lab it's kinetic, in which case you should be doing a constant velocity, where your friction force is going to be exactly equal to the force you pull. So you're going to pull with a certain force, keeping it at a constant speed, and then whatever that force is to maintain a constant speed is the number that goes right here. And of course the normal force is just your mass times gravity. But let's go through an example like with old Meemaw here. So Ferd wants to find the coefficient of friction between Meemaw's chair and the ground. He measures the force he applies as he pushes the chair. Now, measuring force, you might say, how do you do that? Well, in the laboratory, use the little spring scales, right? I don't know how Ferd did it. Maybe he had a massive spring scale. He applies as he pushes the chair with a total mass of 75 kilograms. To just start the chair moving, he applies 350. That tells me that's going to be his static friction force. Then to keep the chair moving, keyword steady pace, 280 newtons. And like I say, most of the time, this number should be lower than the starting moving. So to use that information to find the coefficient of static and kinetic friction between the chair and the floor. So just looking at this, there's a lot of information on the page. I know you want to write, but maybe just pay attention for a sec. His applied force is 350 newtons. If he's just starting to get it moving, that's equal to static friction. And then later on when he's at a steady pace, and that is key, steady pace, and then we can say that's equal to his kinetic friction. So if it takes 350 newtons to just start moving the chair, then 350 newtons must be the force of static friction. And if 280 newtons can move the chair with constant velocity, again, that's really key, then the force of kinetic friction must be 280. So looking at the free body diagram, you know, he's pushing this way, applying 350. So the static friction, which is backwards, is going to be 350. What is the normal force? It's going to be equal to gravity in this case. And gravity is equal to 75 times 9.8. Mass times gravity. I'm going to move on. I know you're probably still writing, so pause, please. So to find the coefficients then, we've identified then that we know Fs and we know Fk and we know normal. So to find the coefficients then is pretty easy. For the coefficient of static friction, it's going to be the Fs, which is this one, divided by normal. And for the coefficient of kinetic friction, it's going to be the Fk divided by the normal. So you can see it's a little bit lower. Oh, geez, error. That's going to be a K. The coefficient of kinetic friction should be lower than the coefficient of static friction. And that is in fact the case. And also, the numbers should be between 0 and 1. So we met both of those requirements. And remember how I said coefficient of friction has no units? That's because in this calculation, if you look at it, I've got newtons on the top, newtons on the bottom. It's like they cancel each other out. So that's why the coefficient has no units. So where did the numbers come from again? The force of static friction is the force he applies to just get it moving, okay? And then the normal force is just mass times 9.8. The force of kinetic friction is the force you apply to keep it moving at a steady pace. Constant speed. Because if you're accelerating it, you could be pulling a lot harder to speed it up. And then you're like if it wasn't a steady pace, excuse me, I'm going to go backwards. If it wasn't a steady pace and I was looking at Fk, then this vector would be way longer than this vector. Okay? And then you couldn't just say, like the only time that they're equal and opposite or balanced is if your acceleration is 0, your net force is 0. So in order to find your kinetic friction, you have to have it at a constant pace so that you have a net force of 0. Okay, I think that's it. So that's the end of that one. Again, there's some good hard questions, and the lab of finding the coefficient of friction between your shoe and the lab bench is coming up.